Hello, class. Okay, so we're going to talk about sound waves and look at the intensity of some sound waves. So the book has a table here. Obviously, you don't need to memorize this information, but here it shows you like certain sources of sound, like a whisper, normal conversation at a distance of 1 meter, rock concert. These are the intensities in watts per meter squared. And there's a couple things that are just really amazing about this table. So at this lower end here, and lower in terms of intensity, the top of the graph, threshold of hearing is 10 to the minus 12th power watts per meter squared. So that's the first amazing thing about this table. This is 1 trillionth of a watt. And remember, a watt isn't all that much. It's a unit of power. It takes 60 watts to run an old-fashioned light bulb. So again, we're talking 1 trillionth of a watt per meter squared. So your ears can detect this. Now your ears have this membrane that can oscillate from differences in pressure. And obviously your ears are less than 1 square meter in size. So you're able to detect, less than a trillionth of a joule of energy is something your ears can detect. And now I should point out, I'm not entirely sure how ears work. I know you have an eardrum, which is a membrane that can oscillate, but there's also like fibers in your ear that can detect, or they play some role too, but in any event, I think we can safely say that your ears are less than 1 square meter in size. So we're talking about 1 trillionth of a joule. And a joule is a kind of a small unit in itself. So your ears are unbelievably sensitive when it comes to just detecting sound. But the second really amazing fact is your ears can also detect the threshold of pain here. That's 10 watts per meter squared. You can hear this as well. You can hear anything in this range from 1 trillionth of a watt per square meter to 10 watts per square meter. So this is like one instrument that can detect sounds with intensities that vary by a factor of 10 trillion, from the least intense sound to the most intense. It's really amazing to have one instrument that can do that. And of course, the reason it can do that is because it's hooked up to a very sophisticated computer, which is your brain. So, yeah, pretty amazing that how sensitive your ears are and this enormous range of sounds that it can detect. Now, of course, this threshold of hearing, that depends on the person. If you're hard of hearing, you probably won't notice this. Some people with good hearing, but this is kind of like an average value. Now, when you get up to something like a rock concert, obviously this can be very damaging to your ears, particularly over long periods of time. So, like if you're just exposed to a rock concert for a second, it might hurt your ears, but you'll be fine. But if you stay there for hours, that can cause some damage, particularly if it's very loud. Yeah, I've had that ringing in my ears after concerts that lasts for days. Probably not a good thing. And then threshold of pain, yeah, you want to avoid this. This is going to cause some serious damage to your hearing. But, yeah, the damage time is a big factor there as well. Okay, so this table, you can always look it up if you need to. On an exam, you'll be given this if you need it. So I'm going to erase it. But before I do that, let's just look, if we talk about the intensity of a sound wave, we've got this enormous range of numbers to deal with. So what we're going to do is we're going to design a scale that's going to bring these numbers kind of down to earth. So we're going to find a scale. I'm going to write this down. This is a Greek letter beta, stands for the intensity level. And the units are decibels, which we write as dB. And we define the intensity level, or the decibel level, as 10 decibels times the logarithm of I over I naught, where I naught is the threshold of hearing, which was 1.0 times 10 to the minus 12 watts per meter squared. Okay, now let's look at the threshold of pain. I'm going to call that IP, or a threshold of pain. Remember, the intensity there was 10 watts per square meter. And the threshold of hearing, we've got that written down here. So let's look at why we would design a decibel scale like this. Let's calculate the decibel levels for both the threshold of hearing and the threshold of pain. So let's start with the threshold of hearing. So we have 10 decibels, and then we'd have the log of the intensity, which is I naught, over I naught. And we can see that this is kind of a very logical choice, having this fraction here, because remember, well, this number here is just 1, and remember the logarithm of 1 is 0. And so basically by defining the scale this way, we're saying that the lowest sound we can hear has an intensity level of 0. That's very logical. Threshold of hearing, 0 decibels. That's a typical person. You can hear 0 decibels, but that's it. Can't go any lower than that. Now let's look at the threshold of pain. So we have 10 decibels. And then we'd have the logarithm of the intensity for the threshold of pain is 10 watts per meter squared. And the threshold of hearing is 1.0 times 10 to the minus 12. And again, the units cancel out. They're both in watts per square meter. So remember in the previous video, we were talking about logarithms. I kind of went through how we would calculate with them, where we'd use a table of logarithms. You might have been wondering, why would we do that if we're not going to actually do that ever in your life, most likely. Although I'd encourage you to give that a try. Carry around a table of logarithms. No one's going to listen to that, but yeah, it can be, make your arithmetic much better doing that. But anyways, we're going to work with, like, you could at this stage just go to the calculator and plug this in, but I guarantee if everyone in the class tried to calculate this number using their calculator, at least a third, I would say, would get it wrong because of the order of operations. Like if you just say 10 divided by 1 to the 10 to the negative 12 power, that's not going to work. You always have to be careful with the order of operations. If you did 10 divided by 1, if you just did this in your calculator, actually maybe this one would work because it would do the, oh no, I wrote it down wrong. That's why it would work. But if you just did this in your calculator, you would get a very wrong answer if you just plug this in. What you would get here is 10 to the negative 11th power. Okay, so yeah, if you just plugged it in your calculator like this, you'd get 10 to the negative 11th power, which is very much wrong. And the reason why is the first thing the calculator would do is convert this into a number. It'd be this part right here would be 0.0001. So you'd have like 11 zeros there and then a 1. And then it would just go from left to right, like 10 divided by 1 is 10. So you'd have 10 times this very small number, which would give you 10 to the negative 11th power. So that's what would happen if you plug in your calculator just like this. Now, to do it properly, you could do this way, and that would give you the correct answer of 10 to the 13th power. So if you do it with parentheses, first it's going to multiply 1 by 10 to the minus 12th power, which is just 10 to the negative 12th power. So what you'd have is 10 divided by 10 to the minus 12. And if you multiply the top and bottom by 10 to the 12th power, you get 10 to the 13 on top. And 10 to the minus 12 times 10 to the 12 is 1. So again, if you don't put the parentheses here, you get the wrong answer. And not just wrong, but very, very wrong. You'd be off by a factor of a trillion. So try to avoid those kind of mistakes. So I recommend in doing these problems to try to do as much algebra as possible, and then plug in, a simple thing for your logarithm. Like save the calculator part to the end. Okay, I guarantee people will get this wrong just plugging this into a calculator. So what I would do here is kind of just what we did before. Let's multiply the top and bottom by 10 to the 12 over 10 to the 12. And that makes the entire denominator equal to 1. So we have 10 decibels times logarithm. So on top we have 10. You can think of an exponent of 1 there. So 10 to the 1 times 10 to the 12. 10 to the 13, and then the bottom is 1. Now here, we don't even need the calculator at all, because the logarithm of 10 to the 13 is just 13. So that gives us our final answer, 130 decibels. So when you look at the hearing range that our ears can detect, the ratio between the loudest sound and the softest sound we can hear is a factor of 10 trillion, where if you look on the decibel scale, the entire range of hearing is from 0 to 130 decibels. So that's a big advantage of the decibel scale. It makes numbers, the scale, much more manageable. Now, there's two kind of disadvantages, or potential disadvantages. One of those is, it involves logarithms, which may be unfamiliar to some of you, and the solution to that, of course, is practice. The other disadvantage is that if you're not really familiar with this logarithmic scale, it can be very misleading. So another thing I'm sure everyone's familiar with, at least vaguely familiar with, that's based on logarithms, is the Richter scale for measuring earthquakes. And again, it's not very intuitive. Like you might hear like a magnitude 6.5 quake, and then what about a magnitude 6.7 quake? Not much different, right? But in terms of energy, there's actually a very big difference between, or significant difference. So even though small differences like say the difference between like 50 decibels and 51 decibels, in terms of sound intensity, that's actually a pretty significant difference. And so, yeah, the logarithms, you just have to get used to them, and that only comes from practice. And same thing with the just the intuitive nature, or more likely the counterintuitive nature, how tiny changes and like the decibels can be the result of significant changes in the actual intensity in like watts per meter squared. And again, the solution to both of those is just work with it until they become familiar. Okay, now let's kind of focus, I mean, I guess in a sense, this is all we really need to do here, but I want to outline a few, the types of problems that we want to, three main problems. I'll just outline two. Maybe we'll do an example of one. But I'll put this here. And I'll just clear the board. So there's two kind of straightforward problems, which I'll just state. And we'll go over examples in class. So one, given intensity, find the number of decibels. So if I say sound has an intensity of 1.5 times 10 to the minus 7 watts per meter squared, how many decibels is that? The other is going the other way. Given decibels, find the intensity in watts per meter squared. So I say a sound of 75 decibels. What's the intensity in watts per meter squared? And those are kind of straightforward, plugging things in. Although for a second one, it's taking an inverse, where we raise it to a power. But we'll go over examples of each of these in class. And then finally, I want to do an example where, let's say we have a speaker here that's producing sound, and you're standing here, and let's say that you hear, let me look at the table, what would be, say you hear 75 decibels. Okay. Now, what if we plug in a second speaker? Place one on top. So they're each producing sound. You're standing the same distance away. They're two identical speakers. So how many decibels are you going to hear now? So the intensity is doubled in this case. So whatever intensity we had here, let's call this I1. Now the intensity in this case is 2I1. So let's figure out how many decibels we're going to hear in this case. Now I'll tell you right off the bat, the answer is not 150. You don't, if you double the sound intensity, you definitely do not double the intensity. Thankfully, otherwise we'd all be deaf by now. Plug in a second speaker, 150 decibels would be very damaging to your ears. But that's not going to happen. So let's call this beta 2. Let's say this one is beta 1. That was 75 decibels. And we want to find beta 2. Okay. I'm going to leave a little room. So let's just plug it in. Beta 2 is equal to 10 decibels. I think I'm going to do this here. I can call it beta naught. I think I wrote this on the equation sheet. We're going to say beta naught is 10 decibels. So, yeah, just a little shorter than writing out 10 decibels in parentheses every time. So beta 2, from our formula, we have beta naught times the logarithm. Now we're looking at beta 2. So we have two speakers. So the intensity is 2 I1 over I naught. Now we can't just plug this in because we don't know what I1 is. Now what we could do is we could write down a formula for I1 and then try to find I1 and plug it in, but we're going to be smarter than that. We're going to use our properties of logarithms, and I'm going to write it like this. Let's divide by beta naught. Different ways you can go through these steps. But if we divide by beta naught, we have, just get rid of beta naught, we have a logarithm here. And I'm going to break this up into two pieces. We have 2I1 over I naught. I'm going to do this off to the side. We're going to write this as 2 times I1 over I naught. So we're looking at a product of two things. So here, using this property, we add the logarithms. So we have logarithm of 2 plus logarithm of I1 over I naught. Okay, so I'm going to erase this. And now, let's just continue. Now I'm going to multiply by beta naught again. Sorry, logarithm of 2. Sorry, beta 2 is beta naught. I'm going to write out 10 decibels. Okay, now logarithm of 2 is 0.3. Very close to that. Let me just, I usually just do 0.3, but logarithm of 2, 0.3010. Yeah, so 0.3, definitely good enough. So logarithm of 2 let's do this, 0.3. And then we have plus 10 decibels times the logarithm of I1 over I naught. Okay. Now, this is very well known. This is just beta 1. If we look at this case, using our formula, beta 1 would be 10 decibels times the log of the intensity, which we called I1, over I naught. That's exactly what we have here. So what we have is 10 decibels times 0.3, that's 3 decibels. And then this part here is 75 decibels. So beta 2 would be 78 decibels. So we doubled the sound, and that added 3 decibels. So again, not the most intuitive thing. Now, let's do this one more time. Let's double the sound again. So I'm going to erase this. let's erase everything. So by doubling the sound again, let's say we have 4 speakers now. So here, we've got 4 speakers. There's kind of 2 ways that we could do this. We could call this 4I1, or we could define I2. Let's do it this way. I2 is 2I1, so we can say that this is 2I2. I think it'll be a little more instructive to do it this way. So let's call this I3. Or maybe we should call it I4, just because there's 4 speakers. Yeah, let's call this I4. That's 2I2. Then we'll call this beta 4. So the subscript is the number of speakers. Okay. So now we have 4 speakers. So we could say that's 4 times I1 or 2 times I2. And if we do it this way, we're going to see the exact same steps apply. So let's do this. We have beta 4. I'll just leave it as 10 decibels. Times the logarithm of 2I2 divided by I naught. And we can write this as 10 decibels times logarithm of 2 plus logarithm of I2 over I naught. So we're looking at what's in the parentheses here is a product of 2 things. 2 and I2 over I naught. And so we have log 2 plus log I2 over I naught. And then here, log 2 is 0.3. So we're going to get 3 decibels, after distributing this 10 decibels. And then for the second term, we have 10 decibels times logarithm of I2 over I naught. And this is beta 2. We have the intensity for this case. So basically we have 3 plus 78. So we have 81 decibels now. So basically every time you double the intensity, you're adding 3 decibels. So if we went to 8 speakers, we'd go up to 84 decibels. If we went to 16, then we'd have 87. And then for 32, we'd have 90 decibels. And so, imagine, 32 speakers. We multiply the intensity by 32, and the decibels go up by 15. So it's a very, this logarithm, it's a very slowly rising curve. Remember we plotted it? So not always the most intuitive thing, but it's a good problem to go over. Just look at the effect of doubling. Every time you double the intensity, you add 3 decibels. And again, we'll go through some examples during the review, but for now, I think we'll leave it here.